All right, cool. So again, these problems here are going to be surprisingly easy to calculate. They're just incredibly difficult to interpret. And it's not that they're incredibly difficult, it's just that we're not used to doing that. And here it's absolutely necessary. So I like to go through and I like to give these meaningful words. I don't let the math control me. I try very quickly to try to control the math. So in these situations, this is what it's asking me about. Let's start to attach some words. Tell me what integral means.
It means the total, the area.
Good. I like that. Total area. Excellent. Total area.
Mm-hmm.
Talk to me about this right here. Do we know anything about that yet?
That's like the total. Didn't we say it was like speed or like change?
Sure. We can kind of justify that. Like we'll double check that it's speed. For right now, we could even just call it a curve, right? So it's like the total area under that curve, right?
Mm-hmm.
Okay, good. But if we wanted to, let's like it's asking us to find a total area. Good. I can do that. We could do that through Riemann sums. That's exhausting. We could do that through power pattern if I have a choice. That's great. Otherwise, we'll have to geometry, drawing pictures. We got options, right? But okay, so we'll come back to that. Let's look at this detail that it's just given us. This says that h of x is h prime of x. Again, there's a meaningful word there. Tell me about h prime of x. That means what?
That is the derivative of h.
Derivative. Good. What are we going to give? What's the meaningful word for derivative?
Derivative. Oh my god, I forgot. Hold on. So integrals are area.
Mhm.
Derivative isn't. I forgot. I think it's speed, but I don't think
It
it's
is
speed.
speed. Absolutely.
Okay.
Good. So this is a speed. So what that says is that h of x, little h of x, is a speed equation. So now you've got the enforcement to go back and say like, okay, good. Like even in this problem, it's describing this as a speed. So I'm trying to find the total area under a speed curve, right?
Mm-hmm.
And then over here, it gives me this. What's big H of x? If h prime and little h is speed, what's this big H?
Is that like the velocity, like the curve
That
above?
same thing as speed.
Oh, um, in my head, it's just like the original equation.
Good. Give me a word for that though. Because this says if I change big H, I
Mm-hmm.
get speed, right?
So the opposite is, it's not gonna be distance because distance is the same. Hmm.
Think about it. What does speed change?
Does it change your distance?
It changes your position, yeah.
Yeah. Okay.
So this right here is a position equation. That's a position equation. So now that we've given it all meaningful words, it's like, good, now we're in the driver's seat. Now it's not just a bunch of symbols on paper. So we go back and say, okay, this is asking us for the integral from -6 to -2 of little h of x dx, which we now know from having put labels on things, that this is looking for a total of speed, and then dx is what?
Um, time or
Good. We can think of that as a little change in time. If position tells me where I am, then x is telling me the when. So this is my time. So I'm looking for a total of speed times time. All right. So again, we're just breaking this on down. Speed times time is
distance.
distance. Good. So I'm looking for a total distance. That's all this is asking me for. Is this entire problem is asking me what's the total distance I traveled, right?
Mm-hmm.
All right. Total distance. Well, total distance, I have position. Position tells me where I am. So if this is asking me for my total distance between -6 and -2, at -6, I was at -6 over 2 in absolute values. That's the where I was. That was my initial position, right?
Mm-hmm.
And then I could say, okay, at -2, that's only 2 seconds ago. That would be when I was at -2/2 in absolute values. That would have been my what?
Um, like the initial, like where you were.
I already have the initial. That was when I was earlier.
Oh,
6
that's
seconds
where
ago
you
was the
ended.
initial. That's the final. Very good. This is the final position. Final position. So let's double check. Is it true that the total distance is the final position and the initial position?
Yes.
Close. Adjust it a little bit. What am I missing?
So I'm sorry, another attorney just walked in.
That's okay.
Can you repeat the question again?
Yeah, so this is saying I've got final position compared to initial position, right?
Mm-hmm.
How do I compare them? Do I add them?
No, you have to find the area of it, right?
Take a look at the story. Total distance is final position. How do I compare
Oh,
that to initial position?
you're adding them.
Okay, so that means that if I was 10 miles from my house, and then
Mm-hmm.
later I was 20 miles from my house, that I have changed between them by 30 miles. That doesn't seem right.
No, you'd only change by 10 miles.
So what's that math? What's the math that goes along with that?
Subtraction.
It's subtraction. It's that it's 20 minus 10 gets me the difference, right?
Mm-hmm.
So here, if I have something that tells me final position or initial position, I need subtraction. That's the last little bit.
Okay.
So all of this comes down to it's saying, what is my total speed times time between these two moments? And we say, well, the total speed times time between the moments is going to be where I was versus where I am subtracted. That's it.
Mm-hmm.
So it becomes absolute value of -1 is +1, and then minus absolute value of -3 would be +3. So we've gone down 2.
Okay.
Now here's what, let me give you some pictures to help kind of back this up. So if we have, let's graph absolute value of x divided by 2. That would be x divided by 2 means that I have brought my x-axis in to half its length. That means that I have something that is appearing as if it is stretched to twice as long. So I took my V-shaped graph and I stretched it to twice as long. This is my graph of absolute value of x over 2. Are we good with that?
Yes.
All right, so this is my big H of x. To remind ourselves of a story, this is telling me my position, right?
Mm-hmm.
And we said very early on that this is looking for my total distance, right? My total distance across these two moments. Let's go back to -6. -6 versus -2. At -6, I had a height of 3.
Yep.
And then at -2, I had a height of 1.
Yep.
Does it make sense that between -6 and -2, I went down 2 units of position?
Yes.
So this one works out quite well. So you have the right idea of like the integral is the area under the curve. It's just that it'd be the area under the speed curve, right?
Mm-hmm.
This one here is a position curve. So I don't need to do the area under this curve. I could make a speed curve and then I could do the area under that. That would be fine. Or we can interpret it through its story, and the story turned out to be a little easier. If you want to make the speed curve, we absolutely could, because take a look at how this is changing. Let me get some space up here. This is changing as a slope of what? What's the slope here?
It's going down by 2.
It's going down by 2 over 2. So that would be, or sorry, 2
Oh.
over 4. So it's going down by a half, right?
Yeah.
Okay, good. So if I wanted to make a speed graph, the speed graph is that it's at going -1/2 for its speed in this region, right?
Mm-hmm.
And then after that, it looks like it flips and it starts going positive 1/2. So then it'd be going this speed. So I've got a weird speed graph. If we wanted to graph that, that'd be fine. And then we could find the area underneath this curve, the area under this curve from -6 to -2. If I did that, that would just be this rectangle, right?
Yes.
What would that be? It'd be a width of
-4, or like a
a
width of
width of
4.
exactly, yep, 4. It'd be a width of +4.
Yeah.
It'd be a height of
-1/2.
-1/2. So I could also have looked at it through this storyline, and if I said that I want that area is width times length. The width here you said is 4. The height is -2 or -1/2. That also would have got us there.
Oh, I see.
So you can absolutely think of it as an area under a speed graph. We didn't have a speed graph. We could have made a speed graph and it still would have got us that answer. Or we just read it through the story and realize that I didn't have to make a speed graph just to find the area, that was literally going to take me an integral versus a derivative. That's just taking me up and down the same ladder. I don't have to go up the ladder to come back down the ladder. I can just stay on that rung and look at my position.
Yeah,
Does that help?
that helps a lot. I was making this way more complicated than it actually was.
It's like this is the best way that I have to approach these problems. Otherwise, I mean, if you bought the book for this class, like take a look when it talks through the like the Fundamental Theorem of Calculus. It's horrible. I hate it so much. It's even worse in the Calc like in the Calc 1 textbook. It's just atrocious. Like they don't do any of this. They do so much they make it so much harder, I think, than they have
I know,
to.
like I was like trying to like watch videos online, and I was like, where is this stuff coming from? I'm like, I don't ever remember us talking about any of this.
No, that's why I don't link to it. Like I'll link you all plenty of things that are very like other people's perspectives for this one, but I kind of refuse to do it for this section because like I have never found another person who's explained it in this way, and I think this is the simplest way to explain it.
I said, this is so easy compared to all the formulas and everything they're giving out. Like, that's what I say. Like, I was making it way more complicated than it actually is.
Like this right here, that right there is your book.
Yeah.
Like it's already pretty intimidating. It's nothing compared to if you actually look in a Calc 1 textbook. In a Calc 1 textbook, it's just stupid. Like don't feel bad about it. It took me years. It took me years to simplify this. Like from having tutored for like 12 years, I think I only started teaching this way 2 years ago. Like because it took me a long time to actually go back through, because in all honesty, I didn't understand it. Like I had no idea. And I was talking to people and they were just throwing proofs at me, which I just consider to be algebraic intimidation, right? Like it is because of course it is. You can't argue. Look, I win. Like that's not helpful. And then like finally I was like, oh, okay. Like if I actually go back to the story, this is not bad at all. So here's the that's the calc textbook.
Yeah, that's like what you showed us like in class at the end of the one. I was like, it looks so bad.
It's so much, and it's not intuitive, and that's why people forget it. In fact, I've actually shown grad students like this method, and they were like, I didn't even know that's what it was talking about. So like they could do it, they just didn't know what they were doing.
But it's easier to like understand, because then you can go back and like you show me or like check it. You're like, well, if you do 10 to 20, like it's not 30, like then it makes sense.
Like, doesn't it make sense that if I wanted to look how far I travel, I look at my speedometer after and then at the beginning of my journey? Like how I've been doing it.
Yeah.
How, like, I remember my dad doing that when we took road trips. Like he'd set the speedometer or set the odometer, right? And then look at the odometer across like the road trip. And he'd be like, look, that's how far it was. And I'm like, that's the fundamental theorem of calculus, bud. Like we could go through it trying to add up the speedometer versus hour time increments, or we could just look at the difference.
Yeah.
So, yep, there you go.
Oh, thank you so much. I have to leave now.
No problem. Send me any more questions over email or bring them to class tomorrow.
Okay, thank you.